Hello everyone, thank you very much for coming. My name is Katarzyna and I'm a computer science student at the University of Warsaw, and I would like to share with you what I learned last year at my internship at Codilime. Okay, we have a problem because you can't see the presentation. I did it together with another intern, Paweł Goliński, and it took us 3 months to prepare a few deep learning models for super resolution. What we did was search for the available published solutions using deep learning for single image super resolution, and we managed to reproduce the results shown in the papers. Who knows what is actually super resolution? Okay, quite a lot of people. Basically, it's a problem when you want to retrieve the high resolution image corresponding to the low resolution one you have. We don't have such good techniques, but still I think the results are quite nice. You'll see in a moment. The problem is hard because it's ill-posed. There exists more than one high-resolution images that correspond to the same lower resolution image. First of all, we wanted to reproduce the results in the paper, so we need a metric. What we used was peak signal to noise ratio, which is commonly used in super resolution papers, commonly used metric, which measures the ratio between the signal strengths. When we talk about images, it's the maximal pixel value in the image. The ratio to the noise strength, which is expressed as a mean squared error, it's computed pixel-wise. So we have the metric. We need also some benchmark data sets. And what is commonly used is the set 5, set 14, and Berkeley segmentation data set. These are the data sets that most papers refer to computing the average PSNR on these images. Well, especially pay attention to the butterfly, because when you search the super resolution papers, you're gonna see this exact butterfly a lot, compared over and over again. When you want to resize the picture, first thing you can do, which is really easy and which is very easy, you can interpolate between the pixels. The 3 basic methods are the nearest neighbor or bilinear interpolation. But the results are not very good because they are just blurry, no sharp edges. So what you can do? It turns out you can take just a very shallow neural network, train it, and have much better results than the bicubic interpolation. This is the first deep learning model that tackled the super resolution problem. The model takes as an input already the big image, but in low quality. And it turns out that okay, we can have the good results, but it's really hard to train the network because it is so simple, no regularization, no batch norms. So we had a lot of problems with this network. What you can think of is maybe the mean squared error is not the best thing you want to optimize. Because it's pixel-wise. It's like for a human, it doesn't matter if you have the sharp edge 2 pixels to the left or to the right, but for this PSNR metric, it really matters. So maybe you can somehow compare the human perception of an image. So who of you is familiar with perceptual loss? Okay, a few. So the next thing we tried is using perceptual loss, which is based on the idea that if we take a neural network that is trained for image classification, it has in its waves encoded the information how the details of everyday common objects look like. So maybe we can take the output of some inner layer from this network and try to match these outputs between our network output and the target image, the high resolution image. The network we used was VGG616, and below you can see the image from the paper that introduced this idea in context of the super resolution. They checked how you can reconstruct the image using different layers, and you can see that the further the layer, the more actual shapes are lost, and you have only the general idea of what's on the image. We wanted to reproduce the paper, so we needed to take the actual architecture that was in the paper. So here you see that the network is more complex. It uses residual blocks and the transpose convolution, which is layer for upsampling, which is learnable. It's not that we take the deterministic interpolation, we do the transpose convolution. And also you can see that most of the computation is done on the lower resolution image, and you upsample the image at the end of the network. So we achieve something like this with. So it's quite good, but it has a really low PSNR because of the artifacts you will see in a moment. But still, I think it looks pretty good. Well, so how you can justify this method in a paper? Has anyone heard of mean opinion score metric? Okay, so it's a metric uses just people's opinion. A lot of people are shown 2 pictures and they say, okay, this one is better or this one is better. And you can score some points for these pictures, and you can show that, okay, so our network performs better in terms of human perception, although the PSNR metric is lower. Okay, so here are the artifacts. Actually, we got much worse artifacts than those shown in the paper. But in the paper, they shown only a few pictures, so, well, we actually don't know if it's the same thing. And first thing we thought of, okay, maybe it's because of the transpose convolution, because it is believed to create checkerboard artifacts. So we used another approach to get maybe better results, and we get better results, but we didn't get rid of the artifacts. The other approach is just do a simple interpolation and then follow it by a convolution. So you can see the artifacts are still there, and we think that it's probably it's because of the perceptual loss doesn't pay attention to such low-level, let's say, textures. Another interesting upsampling layer is something called subpixel convolution, which is very sufficient in terms of the computation time. And it turns out it's basically the same thing as transpose convolution, but you group the parameters in a different way, and it learns differently, and it doesn't produce the checkerboard artifacts. But still we used this layer for upsampling, and we also get the artifacts from the perceptual loss. So we believe that it's because of the perceptual loss itself. Okay, so I think, okay, so maybe we'll switch back to optimizing the mean squared error, and we took the last year's state-of-the-art model, which is our ResNet, which is a much deeper network. It has 16 residual blocks, also a skip connection, also a parametric ReLU, which is similar to liquid ReLU, but the parameter is also learnable. They also use this newest upsampling layer, the subpixel convolution, and we can see that the results are, well, pretty good. And as far as I know, it was the best result in terms of the optimizing PSNR. So here is what we achieved. It's you can see the bicubic interpolation as this benchmark which we want to improve, and those three models. Well, all of them seems in a way unnatural, but we can see that they have these sharp edges. Okay, so what about the textures? Because the optimizing mean squared error leads to overly smooth images. So one of the solutions is to use generative adversarial networks, which again does not score high PSNR because of the textures they generate, because they don't match exactly pixel to pixel with the original image. But you can see that this is, well, this looks more natural. We did all of this in PyTorch, which was a really, really nice experience, because when we started, we didn't know anything about PyTorch, and we just went through the examples on the page, and it turned out that there are already implemented examples like super resolution, actually with a different architecture that we had, but we had for free the data loader, which is, well, in this case, it's not very, it's not a standard one because it's not a classification problem, but, well, it's not very complicated. Generally, the problem of datasets for this for super resolution is it's not hard because we can take actually any dataset with no labels. You just downsample the image, so you have the input and you have the original image that you downsampled, which is your target. We use the MS COCO dataset, but actually we could use any other. But back to the PyTorch, you have also the pixel shuffle layer, which is not trivial in implementation when you want to do it by hand, but it's already there, so it was very convenient. And also in PyTorch examples, there was this fast neural style, which uses perceptual loss. The perceptual loss for the style transfer is a little bit more complicated than for super resolution, but well, it was in our advantage because we just cut out some parts of the code and we had the working perceptual loss. So okay, so that's all. Thank you for your attention.
Okay, so questions.
Okay, so I would like to ask you if you applied your super resolution models to the real images taken by two different cameras, for example, because usually you take a photo, high resolution photo, and degrade it in various ways. Then how can you be sure that you do not learn the inverse transformation? So the way to test it is to take two cameras, one with the high resolution and one with the low resolution, take two images of the same scene and try it. And it's not usually done in papers because it's pretty hard. So have you tried it, maybe?
No, sadly we didn't. What we did, it was trying the model on the noisy images, and well, it turned out that the noising is a crucial step. You can't just take the super resolution model and upsample the image, which is noisy, because it upsamples the noise itself. That's what we did.
I have a question because you mentioned some data sets that you used. So I assume you downgraded the images by yourself using some interpolation for the low resolution images. I assume you used only one type of interpolation for whole data set?
Yes, we used bicubic interpolation for downscaling because it preserves the most information.
Okay, because I was wondering if you could use many different interpolations in one data set, for example, bicubic, linear, and Lanczos together.
Yeah, actually we did some experiments on that. We used bicubic and bilinear, and we also used some data augmentation like Gaussian blurring, but well, it didn't change much the results. So.
Okay, thank you.
What sizes of images did you use? I mean, did you reshape images into one single size, or?
No, we cropped images. I mean, if we resize the images, well, that wouldn't work well because you have two resizings which may distort the image somehow. What we did was random crops. We cropped the image about 100 per 100 pixels and trained the network on that.
Any other questions?
So I have a question regarding the first neural network that you show us. So I know that it does not contain the transposed convolutional layer at the end of the architecture, right? So I assume you need to upscale the image by yourself using interpolation, right?
Yeah.
So if you use the bicubic method and if you train your network with the bicubic interpolation, right? So what happens if you use the image that was upsampled with some other type of interpolation on this network?
Well, we didn't try that. It was part of the method that was described in the paper.
Okay.
I mean, the network consists of the bicubic interpolation, which is not learnable, and then the 3 layers.
Okay, thank you.
Any other questions? Okay, so thank you very much for your speech.